Ever wondered how crystals form? Well, you're about to learn about the fascinating process known as crystallization. This is a process that can be seen both in nature and in laboratories across the globe. Crystallization is the birth of solid crystals from a homogeneous solution. It's a little like magic, turning something liquid into a solid, intricate structure. But it's not magic, it's science. Crystallization can occur in a variety of ways, and it's responsible for creating many of the beautiful and diverse crystals we see in the world. From the sparkling diamonds that adorn jewelry to the salt crystals that flavor our food, crystallization plays a crucial role in many aspects of our lives. But what makes a crystal a crystal? How do they take on their unique forms and structures? Well, those are excellent questions. Now let's delve deeper into understanding the various parameters that define a crystal. So, what are these crystal parameters we're talking about? Let's delve into the world of crystals, where each one, like a snowflake, is unique. This uniqueness comes from certain parameters, like crystal forms, habits, and lattice angles. Crystal forms refer to the external shape of the crystal, which can be as simple as a cube or as complex as a dodecahedron. This form is determined by the arrangement of atoms or molecules within the crystal. For example, salt crystals are often cubic because of the ways sodium and chloride ions arrange themselves. Next up is crystal habits. Now, this isn't about a crystal's daily routine. It refers to the common or characteristic shape of a crystal or an aggregate of crystals. Crystal habit can be influenced by environmental factors during the crystal's growth, like temperature and pressure, or by the presence of impurities. For instance, quartz can form six-sided prisms, or it can form a mass of tiny intergrown crystals depending on its habit. Then we have lattice angles. Essentially, a crystal lattice is like a three-dimensional grid where each point represents the location of a particle. And the lattice angles are the angles between these grid lines. These angles are critical because they determine how the crystal structure repeats itself in space. For example, in a cubic crystal, all lattice angles are 90 degrees. So why do these parameters matter? Well, they're not just scientific jargon. They are key to determining the unique properties of each crystal, such as its hardness, cleavage, and even its color. These parameters are what make diamond the hardest known natural substance and give amethyst its stunning purple hue. Understanding these crystal parameters allows us to predict and manipulate the properties of crystals, making them incredibly useful in a variety of fields from electronics to medicine and even jewelry. These parameters are not just fancy terms, they are crucial in determining the crystal's properties. Remember, each crystal holds a world of complexity within its seemingly simple structure, and these parameters are the keys to unlocking that complexity. But how do we analyze these beautiful structures? You may wonder. Well, we've got a few tricks up our sleeve in the world of crystallography, and today we'll be focusing on one of the most common and effective methods: X-ray diffraction. X-ray diffraction, often abbreviated as XRD, is a technique used to determine the atomic and molecular structure of a crystal. In other words, it's like having a magnifying glass that can see right down to the atomic level. Imagine being able to peek into the very heart of a crystal, witnessing the precise arrangement of atoms within. That's the power of X-ray diffraction. The process of XRD begins by illuminating a crystal with X-rays. These X-rays are then diffracted or scattered by the crystal lattice, the repetitive array of atoms within the crystal. This scattering produces a diffraction pattern, which is like a unique fingerprint for each crystal. By studying this diffraction pattern, scientists can glean a wealth of information about the crystal. They can determine its crystal system, the lengths and angles of its unit cell, and even the positions of its atoms. It's like solving a complex puzzle, with the diffraction pattern providing crucial clues. But here's the fascinating part. The diffraction patterns are not just random scatterings of X-rays. They follow a specific law known as Bragg's law. It's this law that allows scientists to decode the diffraction patterns and unlock the secrets held within the crystal. Isn't it amazing how much we can learn from something as simple as a beam of light bouncing off a crystal? It's a testament to the power of scientific inquiry and the intricate beauty of the natural world. Remember, X-ray diffraction is just one method of crystal analysis. There are other methods too, like neutron diffraction and electron diffraction. Each method has its own strengths and weaknesses, and the choice of method often depends on the specific properties of the crystal being studied. X-ray diffraction, although sounds complex, is an incredibly insightful method of analysis. So next time you marvel at the beauty of a crystal, remember that there's a whole world of atomic wonder hidden within, waiting to be discovered. Ever heard of Bragg's equation? If you're curious about the world of crystal analysis, this equation is a key player. It was developed by father and son duo Sir William Henry Bragg and William Lawrence Bragg, and has been used extensively in the field of X-ray crystallography. Bragg's equation, in essence, allows us to understand the arrangement of atoms within a crystal. It describes the relationship between the angle at which X-rays are diffracted by a crystal lattice and the wavelength of the X-rays. Here's how it goes. N times lambda equals 2 times d times sin theta. N is the order of reflection, which is a whole number. Lambda is the wavelength of the incident X-ray. D is the distance between adjacent planes in the crystal lattice, and theta is the angle of incidence of the X-ray beam. In layman's terms, when an X-ray beam hits a crystal, it gets scattered in various directions. Some of these scattered X-rays interfere constructively, producing a strong signal. This happens when the path difference between the X-rays is equal to a whole number multiple of the X-ray wavelength. Bragg's equation helps us calculate the exact angles at which this constructive interference occurs. This in turn gives us a peek into the atomic arrangement in the crystal. This equation is particularly significant because it enables us to determine the crystal structure of materials. This has had far-reaching implications in various fields of science and technology, including materials science, chemistry, biology, and physics. For instance, the discovery of the double helix structure of DNA, which won the Nobel Prize in 1962, was made possible by X-ray crystallography and Bragg's equation. So, while we might not be able to see the tiny atoms and molecules, with the help of Bragg's equation, we can make sense of the complex, intricate, and beautiful world of crystals. Bragg's equation, in the simplest terms, makes sense of the intricate world of crystals. Why should we care about crystals, you may wonder? Well, let's delve into their stunning beauty and immense significance. Crystals are nature's artistry at its finest. They showcase a kaleidoscope of colors, shapes, and sizes, each one unique, each one a marvel. From the shimmering quartz to the vibrant amethyst, the aesthetic appeal of crystals is undeniably captivating. They are a testament to the wonders that can be created under the Earth's surface over thousands, even millions of years. But their beauty isn't just skin deep. Beyond their visual allure, crystals hold immense significance in various fields. Let's start with electronics. You may not realize it, but crystals are integral to the technology we use daily. Quartz crystals, for instance, are used in watches and clocks for their piezoelectric properties. This means they generate an electric charge in response to mechanical stress, ensuring accurate timekeeping. In the realm of jewelry, crystals have held a prominent place for centuries. Their vibrant hues and unique shapes make them highly desirable. Diamonds, rubies, emeralds, and sapphires, they all are crystals that have been cherished for their beauty and durability. Even in medicine, crystals find their use. Lithium crystals, for example, are used in the treatment of bipolar disorder. Moreover, the science of crystallography helps us understand the structure of complex molecules like proteins, aiding in the development of new drugs. But crystals aren't just functional. They carry symbolic significance too. Many cultures around the world believe in the healing properties of crystals, using them for meditation, energy balance, and spiritual growth. So you see, crystals aren't just pretty stones. They are a fusion of beauty and functionality, a testament to the incredible phenomena of nature. They are integral to our daily lives, from the technology we use, the jewelry we wear, to the medicine we take. Crystals, though minute, play a massive role in our day-to-day lives. Intrigued by the world of crystals, the journey we've embarked upon today has given us a glimpse into their mesmerizing world. We've unearthed the process of crystallization, a phenomenon that transforms matter into an array of geometrical wonders. We've delved into the depths of crystal parameters, exploring their diverse forms, habits, and lattice angles to understand their intricate structure and symmetry. Our exploration didn't stop there. We've also walked through the methods of crystal analysis, particularly X-ray diffraction, and the profound Bragg's equation. tools that allow us to decipher the secrets held within these crystalline structures. And not forgetting the beauty and significance of crystals, a testament to the marvels of nature and science combined. Our exploration into the crystalline world is just the beginning. There's so much more to discover. So subscribe for more, because you won't find me later. Dive deeper into the fascinating world of science with us.